the great thing about a graph is that it allows us to get a picture sense of a particular type of phenomena. In fact, if we have a table of data, we could actually plot the points and actually get a sense of what's happening. Let's take a look at an example. So here we have an ant, which luckily we don't have any ants here because you don't want ants. But there's an ant that's actually walking around, and we actually have the following data. For the time, a particular time, a moment in time, we can see the distance the ant has traveled. So time and distance is given here. Time in seconds, distance in centimeters. So at the beginning of the time, we're going to call that 0 distance from where the ant began. 2 seconds later, the ant is 5 centimeters from where the ant was. 4 seconds later, the ant is 10 centimeters from the beginning, and so forth down the road. Now you look at this, and it's kind of hard to wrap our minds around what's going on here. And of course, a picture is a great way to see what's happening. So if I slide this over to here, we could actually produce a graph that captures this data. So check it out. Here I'm going to graph the ant distance. This also would, by the way, work for an uncle. You see, I made a joke because uncle and aunt, it's spelled differently. Now forget it, it's a joke. All right. Now in the x-axis, I'm going to place the time in seconds, and in the y-axis, I'm going to place distance, which of course is in centimeters. So here's the time, and here's the distance, and we plot x comma y. So the first point is 0, 0. So I plot this point 0, 0. The next point is 2. And then y is going to be 5. So 2 comma 5. Notice the units here, by the way. We have to figure them out. 2, 4, 6, 8, 10, 12. Each of these count as 2. So this is going to be 2 right here. And we go to a y value of 5. And these we count 1, 2, 3, 4, 5. So we go right to here and plot a point at 2 comma 5. Notice the units of measure are a little bit different on the axes. That's completely okay, but we got to be on top of it. 4 comma 10, so x is 4 and y is 10, so I'm at 4, and then I go up to 10 and go over, put a dot there. 6 comma 12, so 6 is here, and I go up to 10, 11, 12, put a dot there, and then 8, 10, 8, and I go to 10, 10, 10, so 10, 10, interesting, same y value, 16, 16, so I get to 16, and I'm way up at 16, and then finally 20 is the last data point, and that corresponds to a difference of distance of 16. Now, I have a whole bunch of dots here that corresponds to this table. Now, the question is, should I connect the dots, make this graph continuous, or should I not connect the dots, in which case it would be called discrete? Well, since we know that the ant was actually walking along as time went on, we know that for every value of time, there's a corresponding distance that the ant has traveled. And so just given this data and nothing else, we could just connect them with straight lines. And so if I try to do that, I'll try to do it right now live, I'll just connect with straight lines. And that's kind of a fun way of doing it, which quite often actually reveals some useful information. So here's that. Then I got a little straight line here. Then I got a little straight line here. A little straight line here. A little straight line here. It's kind of fun to make funny sounds when you're doing it. And this actually represents a continuous graph that depicts what the ant was doing, and we know for sure the ant was at these particular points at those particular points in time. So you can really see that. And we draw in a line to make it a continuous graph since there's motion throughout. Now, let's take a look at another example. Here's one where getting into a park, it's always fun to go to parks, and they have admissions. So it costs $5 per person. So what that means is if you're just by yourself, which is probably not so safe, you should definitely go with some family or friends or something, you need $5. So there it is, boom. Now, if you bring a friend, of course, then it's $5 per person. It means that if you have 2 people, then in fact, you're going to need $10 to get into the park with 2 people. And if you have 3 people, guess how much? That's right, $15. Cha-ching! So we could actually try to graph this relationship between how many people we have and the cost of admissions for those people. And we already see 1 person 5, 2 people 10, and 3 people 15. And now let's see, in fact, by the way, I'm going to keep this for myself for later. So here we have the admissions costs, And on the x-axis, I'm putting the number of people, and then in the y-axis, I have the actual cost. So if no one goes in, how much does it cost to not go to the park? Well, it's free not to go. So if we have 0 people, they'd have to pay $0. If we have 1 person, then it would cost $5. So this is 10, 20, 30, so half of these, this is a 5. If we have 2 people, we saw we'd need $10 to get in. 3 people would require $15. That's 10 and 5 more. 4 people would be $20, and so on. I think you see the pattern. 5 people times $5 would be $25, etc. Now, 6 people, 7 people, and so on. Now, should I connect these with a line? Well, no. This is an example of a discrete graph because it makes no sense to talk about having half a person or 1.5 people. So here we have little quantum jumps of data here with x, and for each of those points, we get the corresponding cost. So we don't connect these. This is an example of a discrete graph. Individual points are islands that actually give us valuable information about this situation involving actual people, and we're not going to cut them up and get fractional people. Anyway, the idea of trying to correspond a picture or a graph, whether it's continuous or discrete, is a powerful way of looking at everything, and we do that, of course, through the lens of mathematics. I'll see you soon.